Okay, good morning. Let's start. Um, since we skipped one class yesterday, so I compressed three classes into two. So we have a very heavy duty today. All right. Okay, first of all, let's review another vector differential operator, okay, which is called the gradient, okay? So the gradient of a scalar field. So we studied divergence, we studied the curl, okay? So now let's study delta, right? So these three, the three differential operator, and the only three differential operator can describe all the variations of physics variables. Okay, so it's sufficient. So we discussed the first three. First three all act on vectors. Okay, let's say divergence act on vectors, right? But the result is a scalar. Okay, then the curl also act on a vector, and then this is the way I remember. So if this is a z, this is a y. So the component of the diagonal term is the same. All right. So this is how I remember. Okay. Okay. Now the gradient act on a scalar field. Okay. Now let's see what that is. All right. Okay. The scalar, let's considering a temperature distribution. For example, the temperature in my office, the current temperature distribution. For sure, at a different location, the temperature varies differently. All right. Now let's see, to describe if the temperature change only with one variable, okay, that's easy, right? So the differential of the temperature change with the location along z-axis is the partial t partial z. So this is just directivity. However, the field we are interested in is three-dimensional. Okay, three-dimensional, we have three variables and x, y, and z. Okay, then how to describe, say, 8.1, I have a temperature I call T1, okay? And then 8.2, which is slightly shifted in X, Y, and Z. Okay, then the temperature is called T2. Then what is the description? Okay, wow, who put Professor Blue's photo as your photo? Interesting. Did you get a copyright? All right, so maybe Professor Blue is much more famous, right? Okay. So you better get the permission from him. Okay, then, okay, by the way, don't put my photo as your photo in other classes, all right? Okay. Then how to describe we call the total differential. The total differential of T. The total differential means, okay, that varies in all the directions we add together, right? Okay, let's say if we define this is a total differential of the scalar field T, right? So that means we have a total variation in x direction, right? Then we have in y direction. Okay, then this is in z direction. Then we add them together. We call this is we call the total. And let me take a look. Maybe somebody put my photo. Okay. Right. Okay. Now we describe all these. We add up all these changes. We add up all these changes as we define as a total differential of the temperature T. Then recall that the dx is a differential length of the total differential length dl. Okay, the total differential length dl. This is a total differential length. Okay, and has a projection. Projection means the projection on x-axis means the dot product with a unit vector. This is unit vector in x, right? Okay, this is a unit vector in y dot product to, you see, because this differential length dl has a direction, right? It's arbitrary direction. Then we have a projection on dx, dy, and dz. Then we replace this okay. We replace this, we can say the total differential. We can write like a dot product of two vectors. Okay, so this is a vector we are very familiar with. Okay, what is this? This is a delta, right? This is delta. Delta is a vector. It's a vector differential operator. Okay, this is operator. That means it can act on any scalar field function or vector field function, depend on you're going to take a divergence or curl or gradient, right? So this is basically a two vector dot product. Okay, this is another vector. dl is a vector, delta is a vector. So I have a dot product. Okay, I can write in this way, right? I can write in this way. Then, in short, okay, we can write total differentiate in this way. Okay, this operator. Okay, this operator, I gave a name. I call gradient of this is called a gradient of a scalar field T, right? Now let's fill up this empty is delta. What is the gradient of phi or delta phi means I take partial derivativity of phi with respect to x, okay, with respect to x, but I have a direction, okay, because each of these will have a direction, right? So I have a direction. This is the x component, okay, then okay, so now we have a complete set of vector differential operator. Okay, divergence, curl, and the gradient. What is this? What is the short name? Okay, that. Okay, that. Then there it is. Let's understand what is exactly, what does that mean? Okay, what does this gradient, why is this gradient is useful? Okay, why is the gradient is useful, right? The gradient is useful. Let's look at this definition. Let's look at this definition. Okay, this definition I can write in this, right? Because DL is a unit vector. I can write like it's a magnitude, and also is a unit vector, right? Okay, unit vector. I can write in this way, or DL. Okay, so I write in this, right? Then, therefore, we have a very clear picture is what this is. This is called the directional derivativity. Okay. What that means is, if I have a temperature field, okay, I like to describe, okay, at a certain point, okay, and if I define a direction, if I define the direction, I will say, hey, how the temperature change in this direction? What is its derivativity in this particular direction? Giving a particular direction. This is called directional derivativity. All right, directional derivativity. Now, after we define the gradient, okay, so what that says is, okay, so if you like to find directional derivativity, that's fine. Okay, you take gradient first. Gradient has no specific meaning for particular direction. Okay, has not mean it describes the variation in all the directions, right? The variation in all the directions. Then this is a vector. You take a projection of this vector onto the direction you are interested in. That become directional derivativity. Okay, for example, if this is my direction of L, okay, then because this is a delta phi, okay, this is delta phi. This delta phi, let me show this vector. This is a unit vector, so I just write like a unit vector, okay. But however, the dial can be any magnitude, right? And then also has a direction, okay. The projection onto this, this is d phi dn. You understand? Okay, so what that means is, if you choose any direction, now you choose, oh, I change my direction. Okay, I change my direction. This is my another DL. I like to find the directional directivity in another DL. Okay, then that's fine. So it says, okay, take projection onto this. This become directional directivity for your new direction you choose. Okay, then what that means is the del tells you the direction of the field change, the direction of maximum change of the scalar potential. Okay, scalar field. Let's take another example. Say when you people in Hong Kong like hiking, right? So the hiking. So if you look at the map, okay, I call the equal magnitude, equal height, okay, altitude map, okay. So let's say this is 2,000 meter, okay, right? So this is a 1,800, okay. So this is 1,600, okay, and so on. So this is our map contour. Okay. Now let's say if you stand here, okay. Let's say if you want to climb, okay, climbing the hill, and then if you like to decide which direction has the steepest slope, what do you need to do? Okay, take the del of the height. Okay, then you'll find that is a direction usually the normal to your equal magnitude curve. Okay, so this is the direction that has steepest slope. Okay. All right, so I go too slow. Now we finished reviewing what is gradient. Okay. Now we have all the tools we have. All right. So this example just a self-study. Okay. Then same as divergence and the curve. You see, just now we derived the del in Cartesian coordinate system. You can also find the del in cylindrical coordinate system and also spherical coordinate system. Right. Okay. So we are going to use this later on today. Right. Now let's introduce a very important or useful vector identity, a useful vector identity. What that means is, okay, for any scalar field V, okay, for any V, which is scalar field, which is because it is a field, that means it is a function of a location, right? Function of location. That you have freedom to take gradient, right? Okay, you take gradient, you have freedom to take gradient, but no matter what, okay, no matter how much freedom you want to have, right? If you take curl of it, it's constantly equal to 0. Okay, you always have a constraint. Okay, the constraint is the curl of any gradient will be equal to 0. right? Right. So you cannot escape from the palm of the God, right? Okay. This is a very important vector identity or the property of that of gradient. Let's see how to. Interesting. It doesn't convert it. Okay. So can you see this part? I guess not, right? Okay. So maybe why convert into, okay, that's fine. So let's assume we take surface integration of this on both sides. Okay. Let's take a surface integration of divergence, of a curl of the gradient. This is a vector. Okay. Then using Stokes theory, we know this equal to, this is the surface. We have, this is surface. Okay. So we have a boundary C. Okay. We already justified this. Right? And let's recall what is this. Do you remember what that is? This is the total differentiate. Sorry, not T, is a V. This is total differentiate, right? So this equal to the total differentiate. That means this is a closed surface. Say that this equal to this, right? This equal to this. So if you have a point in this C, no matter, okay, if this is the normal direction, okay, so this will become a C, okay, the direction of C. So you're starting from this point, okay, so this basically is a way from any P point to the same point, right? The integration from one point, come back. Okay, you're starting from this point and then come back to the same point. Okay, the line integration. So this always equal to 0, right? So this is this remind us, okay, this very important factor remind us for static field, for static electrical field, okay, we have this property, right? You see, because the Faraday's law is this. If the field doesn't change with time, if field doesn't change with time, this equal to 0, right? The does not change time invariant. Time invariant. So therefore, this equal to 0, then this equal to 0. Okay. Then you see the electrical field, the curl always equal to 0. That means the electrical field can be represented. That means the electrical field can be represented by gradient of a scalar field. All right, right? And for convenience, we define, you see, because the electrical field in this direction, if this is a V2, this is a V1, so V2 is larger than V1, right? The V2 is larger than V1. So therefore, Oh, sorry. Uh, so this integration is from, in this case, V1 is larger than V2, sorry. Okay, V1 is larger than V2. So that means the del of V, gradient of V, if it is positive, that is against the direction of electrical field. So therefore, I put minus sign. Okay, because I put minus sign doesn't contradict to this law, right? Does not contradict to this law. So I put a minus sign in to make the definition of potential inconsistent with the direction of electrical field. Okay, so this is for static field, right? So that is one useful vector identity. Now let's look at another useful vector identity. Okay, another useful identity is, so actually we already learned this, is if we take a curl of a vector field, its divergence is constantly equal to 0. Okay, so we proved this using divergence theorem. If you don't remember, and go back to take a look at our previous note. Okay, now we have this important, we have two important vector identity, right? One is the curl of, I can put bracket or not put bracket, you see, because it is obvious, right? It is obvious. This is a vector. Okay, this is another vector. Okay, so vector cross vector, right? So this constant equal to 0. This is the one useful vector identity we are going to use. And another important useful vector identity is the divergence of a curl of a vector also constantly equal to 0. Okay. Now we have these two vector identities we are going to use. Now we define, okay, now we define V. This V is defined as electric we call electrical potential function. Okay, potential is not new to us, right? Because when we study the circuit theory, we have voltage and the potential, right? When you write a node equation, right? When you write node equation, you need to know potential at each node, right? You see, because when you study the circuit, you have, you see, this could be resistance, it could be inductance, capacitance, and so on, right? So those are node we call, right? So, and so on. So those are node, the potential. Then what voltage means? So voltage means the voltage is a potential at node I, okay, minus potential a node G. Okay, so this voltage IG. Okay, so that means if I like to find voltage between, say, if this is I, this is G, so VIG equal to VG minus VI. This is what we learned in circuit theory. Okay, so circuit theory, the potential is relatively to the voltage, relative to the ground, right? Okay, but here the potential function is completely different meaning. Okay, completely different meaning. We are talking about a function. Okay, we are talking about potential function. So we need to introduce two very important potential functions in EM theory. Okay, without introducing them, very difficult for us to solve practical problem. Okay, today we are going to discuss antenna problem. Okay, very small antennas, very small piece of conductor wire. It is antenna. Okay, then let's find out what is electromagnetic field. Okay, and we need to derive the electromagnetic field. Okay, once we understand these very small antennas, once we understand very small antennas, then we can understand any antennas. Okay, we can understand any antennas. So to understand these small antennas, then we need to study these two potential functions. Now you can see how important these potential functions are. Okay, so the first potential function, we already introduced, we call electric potential function. Okay, electrical potential function. And later on, we will iterate this and with enriched meaning. Right. Now let's look at another vector, another potential function. The second potential function is we call magnetic vector potential function. Okay, it is a vector. The first function is a scalar, and this function is a vector. Why it is a vector function? We use this vector identity because magnetic field, okay, for magnetic field, no matter time varying or time invariant, its divergence is always equal to 0. That means there's no magnetic charge. Okay, so any magnetic field line, the ending point and then the beginning point must be connected. Okay, so this is the magnetic field. Okay, so the magnetic field line is always closed loop, but electrical field is different. The electrical field starting from a charge and ended at where the potential equal to 0. Okay, anyway, because this property, then you compare these two. Then if you compare these two, okay, if you compare these two, now what kind of clue we can have? What kind of clue we can have? We can say, oh, the B can be represented by this, right? Because this all divergence equal to 0. Now we define B is this. B is this. Then we call the vector A. We call vector A is called the magnetic vector potential function. Okay, potential function. Now you can see that for electric potential function, you can see we have some advantage we can take. What advantage is electrical field is a vector, but the potential function is scalar. The scalar function is always easier than vector function, right? Then what we can do is we can solve scalar function first, then just simply take gradient. Then we can get a vector field. What convenience we have, right? Great. Okay. What convenience. Now let's look at for magnetic vector potential. It seems this advantage disappeared because magnetic field B is a vector, and your potential A is also vector, right? It's also vector. Then what's the point? We find one vector and then take a curve, we find another vector, right? From that sense, you don't see the advantage, but later on, we can justify the vector potential function A related to the source current generated field, okay? Related to the current in a very simple way, okay? Then we can very easy to obtain the A potential. Then we use this relation, we can find the B field, okay? Find the B field, that means you can find the B field, then you can find the H field, right? Okay. Now it seems you have a scalar, you have a vector potential, you have a scalar potential, you have a vector potential, electrical field and the magnetic field are not related. Then this is a contradict to what Maxwell equations tells us. Okay, what Maxwell equation tell us is magnetic field create electrical field. Electrical field create magnetic field, right? Okay, they're interlaced, okay? But this is not very true. Okay, this is not true for magnetic field. Why is not true? Because how we derive this? This is derived because this equal to 0, right? But this is time invariant. Okay, this is time invariant field, not time varying field. Okay, so now let's go back to take a look what the Maxwell equation tells us. Maxwell equation tells us is Faradays law. Okay, the time varying B is time varying, right? This is not equal to 0. That means change with time. The time varying field generate electrical field. Time varying magnetic field generate electrical field. So this not equal to 0. Okay, not equal to 0. So we substitute this relation into B. Okay, of course we can, right? Okay, then I move this to the left hand side. So we have this equation. You see this? Okay, this basically is B, right? Okay, because curl and the curl, then I can write this. I can write this. Now, this is always true. This is always true, right? This is always true. A vector whose curl constantly equal to 0. That means this term we can represent by a scalar function, right? So that means this can be always represented by a gradient of a scalar function. This function we officially define the general electrical scalar potential function. Okay, this is scalar function. This is always true, no matter if time varying or time invariant. Okay, because if field doesn't change with time, this term equal to 0. So we got the previous equation, right? But in general, it's not. Okay, then now we can say electrical field, this is related to magnetic field. And the two potentials are all related. Okay, vector potential and the scalar potential, they are related. Okay, they are related. So therefore, we can say if we can find the scalar potential phi, we can find the vector potential A, we can find the electrical field. Okay, now the problem for solving electromagnetic field tends to be another problem, is to find potential function. The two potential functions. One is the electrical scalar potential, one is the magnetic field vector potential function, A, right? All right, okay. We were discussing how to find this, right? And before we discussing this, we define another function where we're going to find it is useful. Okay. Good. We have 3 minutes before before break. All right. Now let's define another new operator, but this operator is not independent. It is dependent. We call Laplacian operator. Okay. Laplacian operator, what is this? We define the del, right? The gradient. The gradient is we find the gradient. So this is a vector. Then we take divergence of this gradient. Okay. This become, oh, sorry, I forgot. Okay, so that means I take a second derivative. All right, so this I write this operator. Okay, you see, because this looks like it looks like this, right? It looks like this, so I define as this. So this operator we call a Laplacian operator. Okay, we call Laplacian operator, or this, right? All right. Okay. So now So this Laplacian operator is just operator, not independent, because it is composed by der and divergence, right? So this is the second order differential equation, or the operator, all right? And this is scalar form. We also have the vector form. We also have a vector form because we can justify the vector identity is, if I take the vector form of this, that means each component satisfies this scalar Laplacian operator, okay? So this vector form, we can expand into two terms, okay, into two terms. So this is something useful we are going to use, okay, useful vector identities. And then obviously, if we have electrical field satisfy this in static case, or even not static case, even time varying field, okay, time varying field, the divergence of D equal to the charge, okay. And also we know electrical field can be represented by this, okay. If the field doesn't change with time, I don't care about this, doesn't change with time, and I substitute this into this, we can see we have electrical field potential function satisfy a second order differential equation defined by Laplacian operator, okay? And this equation is a very famous equation we call Poisson's equation, okay? So Poisson's equation also widely used in semiconductor field, you see, because when the scale is so small, okay, in the integrated circuit, and if we like to find the potential distribution into a complicated, let's say, transistor structure, then we need to solve this scalar function, okay, or Poisson's equation in a three-dimensional manner. Right? Okay, let's take a break and then we resume at 10:30. Okay, let's resume. One question I just got is a little bit confusing about Laplacian operators, particularly when it is used for vector field. And it's not difficult to explain what is a scalar Laplacian operator applied to scalar field, right? And then if you consider the scalar field is one of the component of the vector field, say if this is if phi is ax or ay or az, right? Ax or ay or az, then you apply 3 times, right? So this is how we can define a vector differential operator, okay? So this is just a definition, okay? Just a definition, all right? But once you define this, you can prove this is a vector identity, okay? Vector identity okay. So vector identity, we just use it. We don't prove it, right? This part we already discussed. This is part of the divergence theory for in Maxwell equations. This term we just introduced. For electrical field, we can express electrical field in terms of scalar electrical potential function and the vector magnetic potential function A, right? And then if for static field, so this equal to 0, right? Then we substitute this into this, we can have this equation, That's it, right? Then this equation is we call a Poisson's equation. So this equation, Poisson's equation, if you know the charge distribution, okay, for time invariant field, you can find only need to solve scalar field, okay? But the question is, I mentioned in integrated circuit design, you see, if you give you a transistor structure, right, and then you have a gate, you have a drain, you have a source, right, and then you have a terminal, right? Then you have a semiconductor base. Then to solve the electrical field, okay? So to solve the electrical field distribution into this, because scale is so small, okay? The field travel, the wave travel from here to here is so, because distance is so short, so you can consider it doesn't change with time. Okay, so this is just approximation, but this is already beyond the scope of this subject. Okay. Now, let's answer a question. Are vector potential A, scalar potential phi independent? Do they have to be independent? The answer is not. Okay, so this is one thing we need to answer. Okay, immediately. And another question we need to answer is, okay, how to find these two potential functions if we know the source? Okay, if we know the current distribution in free space, if we know the charge distribution, how to find these two potential functions? All right, okay. So, and at the end, you will say, oh, introducing a potential function A bring us a great convenience in solving electromagnetic problem. And then we discuss one example is the relation of very small current dipole. Okay, a very small piece of current that generate electromagnetic field. And what is behavior of electromagnetic field? Okay, to answer first question. Okay, to answer first question. Now we have a field quantity. We have a field quantity. We have a field quantity. So get rid of this. Okay, then we have field quantity is the divergence theory for electrical field. Okay, so we substitute the total expression because this is E, right? We already justified this is E, right? So we substitute this into the divergence equation, right? Then we find this is a Laplace operator we already defined, okay? Then we move this, divergence into the bracket, okay? And change order of differentiation with divergence and derivative with time, right? We just change the order, then we have this equation, right? So they are related, okay? Then we use another equation, the curve equation in Maxwell equations, right? This is epsilon. This is epsilon. So epsilon, we know the epsilon. So I multiply the mu on both sides. Okay, I multiply the mu on both sides. You see, the reason is the mu times h equal to b, right? Okay, so I multiply mu on both sides. So this is b. We already introduced. Okay, the rest of it is very straightforward, right? Because d, the d is the electrical field how to get rid of this. Oh, okay. So the d is this, and also we know the electrical field can be represented by this, right? So this is a d. So you substitute the d. Okay, so that means if you multiply this into this, so this is basically is a d, right? Okay, then from the Ampere's law, we have another equation. This equation using this vector identity, okay, we can simplify it to this. Okay, we can simplify it to this. Now we have two equations. Now we have two equations, right? We have two equations. One is we just arrived, and this is second equation. This is second equation. I copy these two equations, okay? I copy these two equations. So let's take a look. Let's take a look of the relation. Okay, let's take a look of this relation. So what that says is we have two coupled equations, okay? Coupled differential equations. Coupled differential equations for scalar potential, and vector potential, okay? And these two equations not necessarily coupled. The reason is the reason is we define the curl of vector A. Okay, we define the curl of vector A. Okay, curl of vector A equal to B, right? This is defined, but we have a very well-known or very famous law we call Helmholtz theorem. What that means is for any given vector field A, we define a vector V. Define vector field A, we must define its curl and divergence. Okay, we haven't defined the divergence yet. Okay, so that's why we need to have another equation. We need to have another equation to couple, to put a constraint, on its behavior of the vector A. Okay, the constraint of the behavior on vector A, right? So in this case, okay, if we find appropriate definition, okay, or appropriate definition for its divergence, we can decouple these two equations. Okay, how to decouple them? Okay, how to decouple them is then in order to find something related to its curl, take a close look. How about this? If this term equal to 0. If this term equal to 0, this equation, second equation, only relate to A and current G. Okay? And then we can prove the first equation only depend on phi and rho. Okay? Right? You see, because if we define the divergence of A equal to okay, if equal to this, right? So that equal to 0. We also, you see, we have done 3 things, right? First, we define the divergence of vector A. Second, we decouple these 2 equations, right? We decouple these equations. And the third, we find a relation between A and phi in a very simple way, right? So after having this, we have a very simple way. We define 2 potential functions. This is a very famous condition we call Lorentz condition. Okay, we call Lorentz condition. This is constraint. Okay, this constraint. Okay, everything has its own constraint, right? Then the 2 decoupled equation, phi and A. These 2 equations are very familiar to us. What are these? Wave equation. Okay, this is wave equations. So wave equation. Okay, so wave equation. What that means, the potential function also satisfies the wave equations. Okay, also satisfies the wave equations. Now, so the special case, right? If it doesn't change with time, we already mentioned this equation, and also it's clearly, you see, for the vector potential A is only dependent on G. We also discussed this. We learned this in static electrical field and a magnetic field. At that time, electrical field and magnetic field are decoupled, okay? And we also know, because of this Poisson's equation, we know its solution is in this form, okay? And also the vector potential A also satisfies the vector Poisson's equations. Its solution is this. So this is no, okay? Okay, this is no form. Okay, now what is the difference of time varying field compared to static field? Is the solution is always with argument of t minus r, the speed of wave. Okay, so the argument is this: we justify this can be arbitrary function f. And then you can say plus arbitrary function of g, right? If propagating in another direction. Do you remember? You see, we had a solution for Maxwell equation in general, right? So we have these two waves. So that means if I only concern the wave propagate in from this point, propagate outward, okay, in r direction. So I just write in this form. Okay, so that means for time varying electromagnetic field, the potential, if I know charge distribution, okay, if I know the charge distribution, if I know the current distribution, I can find phi and A. I can find phi and A, right? This is the general form if I don't know how it changes with time, right? But for time harmonic electromagnetic field, we introduce concept of phasor. Okay, so what that means is the E and H, they change, okay, they change proportional to cosine omega t plus minus, okay, I use K, right? And then KR, okay? It changes like this. Or if you like, you can add another initial phase constant, okay? So this called time harmonic. Okay, so that means up and down, sinusoidal. The change with time is this, right? Right. So this is we explain. Right. So the omega divided by k is the speed of wave, right? Is speed of wave. So this is inconsistent with this form, all right? Inconsistent with this form. Now we have everything, right? Because we said once we use a phasor, I don't need to write this time convention every time. I don't need to write time convention. So this is because this is a time convention, then time right? Okay, so I don't need to write this every time, but we put it into our heart, right? Okay, so these two expressions can be simply expressed as, okay, these two expressions can be simply expressed as this and this, right? This and this. If we keep this in our heart, right? Okay, so we put this in the heart. We don't repeat this. Okay, we don't repeat it. This tells us is A is very convenient to find if you know current. Because A is so simple, then you can imagine B is the current of A, and related to the source will be in a much more complex way, right? In a much more complex way. All right. By the way, okay, we should, what I need to emphasize, okay, let's show the coordinate. If we have a coordinate, okay, this is a field point. Okay, this is my vector R. Okay, this is vector R. Or if you put the source at the origin, okay, but now we put current here, okay, this is X prime, Y prime, Z prime, okay, this is a source, okay, this is we call R vector, and this is a field point. It's R, okay, it's R. So this is R vector, okay. This R vector is R prime, R minus R prime, okay. So this is what this R is. This is what R is, right? So you can say this integrand, the current has its location, is X, Y, Z prime, okay? But don't forget R is the magnitude of this equal to X Okay, so therefore, this is a function. Oh, sorry, this shouldn't be R. This should be, this is wrong. Okay, conceptually is wrong. Conceptually is wrong. This is a variable of R, right? Because the potential is only related to the observation point. Only related to observation point. It has nothing, because the source point, the R prime point, already integrated. Okay, already integrated. Okay, and then it's already gone. Right? Now we have, let's discuss a very small antenna problem. Okay, very small antenna problem. This antenna problem is described in this way. I simplify, okay, to simplify our analysis, I put this current into the origin, okay? Okay, I put this source at the origin, okay? So R prime basically is 0, right? Because it's so small, this is so small, okay? I put it at the center of the coordinate, right? Then this is so small, this L, the total L compared to wavelength is a much smaller, okay, much smaller. And then I put the 2 end plate. Why I put the 2 end plate? Okay, I magnify this. I have a current. If I don't have end plate, what that is? The current will be equal to 0, right? The current, the magnitude at middle is maximum, and the current is the 2 end, nowhere to go. So of course 0, right? Unless if I like to retain a constant current, okay? If I want to retain a constant current, the current distribution is constant. What I try to do is, okay, I put a small plate with charge, okay? So I have a charge, I have a minus charge, okay? I have minus charge. Then with charge there, because of the current continuity, if you have a, because the current equal to dq dt, right? Okay, right? If you have a charge change with time, then the current is not equal to 0, it is to 2n. Okay, that's why I put, that is why I put two very small plate. Okay, but this plate doesn't participate into the radiation. Okay. And also I assume the current, the wire, conducting wire, that carries the current is very thin. The radius is very small. Okay. Now I describe this current in this way. After I explain you the physics, okay, after I explain the physics, okay, then we can abstract the current in a mathematical form, okay, flowing along the z-axis with the magnitude I0, okay, magnitude I0, constant, okay, constant. Now under this, let's see how we use this, relation, okay? So what this is the coordinate of R, okay? This is the coordinate of R prime, okay? Right, because I put at the center, so R in this case is capital R equal to small r. Right. All right, okay. Capital R equal to small r. So you see, because this is 0, right? So this equal to R, right? Equal to R. Okay. Then for given observation point or field point, for given field point, okay, for given field point. So we know X, Y, and Z. Now we do the integration. Now we do the integration because current is a constant, so I take out. So I only integrate from minus L divided by 2 to plus L divided by 2, okay? From low limit to upper limit and integration along the z-axis, okay? So as a result, that multiply length L, right? Multiply length L. Because this is so small, so this R, okay, this R is constant. Now we can find what A potential is. Once we find the A potential, this potential, when we derive it, is only in X, Y, Z coordinate system. But to describe the field radiated by a small dipole, you can imagine the antenna radiated in all the directions, right? In all the directions. So the best way to describe it is using spherical coordinate system, okay? To analyze the field in spherical coordinate system, we translate the X component in X, Y, Z coordinate system into spherical coordinate system, okay? Then we find the dictionary. We discussed this before, right? So I said you don't need to remember. I can give it to you, or you can find from textbook. This is transformation. Okay, we translate the vector potential function in Cartesian coordinate system into spherical coordinate system. Okay, so in this way, because AX equal to AY equal to 0, okay, we only have a Z component, right? Then we can find AR, A theta, and A phi equal to 0. A phi equal to 0 is unstable because of the symmetry. Okay, so along in phi direction, no difference, right? Now we use the definition of A, right? Because remember how we define the vector potential function is this. Once we know A, we can find the B. B is what? B is mu times H, okay? Now let's find H. H is, take this, okay? Take a curl of A. Curl in spherical coordinate system is this, okay? So this basically you don't need to remember, okay? You don't need to remember. Now we can say, what we can say is we don't have A phi component, so this is A phi component equal to 0, right? And also because of the symmetry, about, you see, this current is in z-axis, they're not differentiate, right, at a different phi. That means partial phi equal to 0, okay? That means partial phi equal to 0. So this equal to 0, right? This equal to 0. This equal to 0, right? Okay? The only component left is this. Okay, the only component left. And we have A theta component, we have A phi component. Okay, we have A phi component here, right? You only need to substitute them into this, okay? So A phi component and the AR component, right? you substitute them into this. All right. So you can find this. So I don't need to spend time on conducting directivity, right? So this is too rudimentary, and then I leave it to you. Okay, so I leave it to you. Now we can see we have two ways to find the electrical field. Okay, we have two ways to find the electrical field. One way to find the electrical field is because electrical field is related to go back. Look at this. Because electrical field, we can find by this, right? So we can find the potential. You see, because we already found A, okay. Then for time harmonic field, partial A, partial T equal to J omega A, right? J omega. Then we need to find the phi, and the phi can be obtained by Lorentz condition, okay? Because of this, right? So partial phi, partial T is J omega phi, right? So this Lorentz gate means the divergence of A equal to minus J omega epsilon mu and phi. This is also we can use, all right? We find A, we can find the phi. We find the phi, we substitute phi in, then we take a gradient of the phi. We can find the electrical field, right? So this is the one way we can find the electrical field. This is one way, okay? And another way, okay, this is one way we can find. This is one way we can find the electrical field using this, where this is a Lorentz condition, right? We can find from A, we can find the electrical field. This is one way. I leave this to you, okay? We will have assignment today. I let you to derive this. And also, by the way, we had a couple of years, we had one question in final exam. Basically, let you to derive this in final exam. Okay. We have another way, I think is a more straightforward way to find the electrical field is what? Is using this condition. What this is? This is Faraday's law. Faraday's law tells us not Faraday's law, Ampere's law, right? So Ampere's law tells us is the curl of magnetic field equal to J plus, okay, plus the time varying electric field. This is a displacement current, right? Or how to calculate this in time varying field is J omega epsilon electric field. Okay, so in our problem, we put a current here, but in our field point, okay, do we have a current here at this point? No, we don't have a current, right? At the field point, at field current equal to 0, right? Field point, current equal to 0. So therefore, using this relation, we know we have this, right? So that means once we know magnetic field, we can easily find the electric field using this. So I think this is relatively straightforward, okay? Relatively straightforward. Then we know the magnetic field R component and the theta component is 0. We only have a phi component. Then we take curl of magnetic field, okay? We can very straightforwardly, we can find electrical field. The electrical field, we have R component, we have a theta component, but phi component equal to 0, okay? For electrical small dipole antenna, we don't have phi component, okay? Phi equal to 0. So it's unstable if you have a phi and also the field doesn't change in phi direction. If you have a phi component, that means you also have a phi component, some phi component. That means the electrical field line in a closed loop, which is against the Maxwell equations, okay? Against the Maxwell equations, because the Maxwell equations tells us the curl of electrical field not equal to 0 when it changes with time, okay? Not equal to 0. So this is equal to 0. That makes sense, okay? So we have a total field. Then we solve this very basic antenna problem. We solved a very basic antenna problem. How basic it is? So how basic it is we have a very, very small current dipole, okay, at any point in three-dimensional space, at any point in three-dimensional space, okay. Then we have R component, we have theta component, which is theta component, R component, but not phi component. But however, we have a magnetic field that has a phi component, okay. The magnetic field has a phi component, right? And then you see the variation with distance of the field. We have, you see, let's look at the E theta, okay. The E theta, we have the field component, we have something 1 over R, right? You see, because once this term multiply into the first term, we have 1 over R. This is 1 over R, right? We have 1 over R square terms when you multiply the second term. Okay, then you have one over R cubed term. All right, 1 over R cubed term. So this is E theta. How about ER? Okay, the ER proportional 1 over R squared. Okay, right? Because the basic term is 1 over R squared, right? And also 1 over R cubed. All right, let's look at H phi. So I use this sign means proportion. proportional to. Okay, what this means? Okay, proportional. They're proportional to. Let's look at H phi. H phi also 1 over R and 1 over R squared. Okay, now let's see. One so when R is approached to infinity, R is a very, very large or not proportional to. Oh, when R is a much, much larger than wavelength, okay? Or not talk about the wavelength. Why it is a wavelength, you see, because we are always proportional to KR. You see, because we are talking about KR. The KR is 2 pi times R divided by wavelength, right? Okay, so if KR is much, much larger than 1, that means than what, right? Okay, or when R approach to infinity, very, very large, okay? So this term goes to 0 much faster. This goes to 0, this goes to 0, this goes to 0, right? 0. What left? Okay, and only H has 1 over R, E theta has 1 over R, right? So that means when R very large, that means our observation point is very far away from the source, and H phi only something, right? That equal to this 1 over R, okay? And E theta we know what this means, right? This is okay. So this is 120 pi in free space, right? And also K times I0, which is current magnitude sine theta. Okay. Then let's take a ratio. E theta over H phi. What are equal to? Okay. That's exactly equal to this, right? And also, if E theta in spherical coordinate system, H phi, and this is the direction of R, right? So E theta cross H phi is a propagation direction, right? And E theta perpendicular to H phi, and both E and H perpendicular to the direction of propagation R. What that means? It is a plane wave, right? It is a plane wave. And the ratio of E over H equal to wave impedance. This is another important property of plane wave. Okay, another important property of plane wave, right? So the only one thing you say is different from our plane wave is our plane wave doesn't include this 1 over R distance dependence. This is because, not because it's not there, it's because when the wave travel say, once we've traveled, let's say 2 kilometers, okay, then you stand here, 2,000 meters, and then another, okay, the wave propagate 1 meter over 10 meters. If you calculate these two numbers, can you tell me what is the difference? Do you see any difference? So not difference. Okay, so that means we don't need to consider the 1/r distance dependence when we talk about in this region. Okay, so this is what I try to say is the plane wave is a solution of antenna when the field travel far away, okay, far away, right? And although the result we derive from a very small antennas, but if we have a larger antenna, if we have a large antenna, okay, say if we have a large antenna, we can chop it into a very small pieces, right? So this, if we know the current distribution, we can use this integration. We can use this to integrate along this C, okay, along the current L. So then this L is prime, I mean the source, okay. I can find A, then I can find, you see, now our logic is we find A, we find H, then we find E, right? And who determines the A? Current. Now you know what creates the electromagnetic field? Current. Okay. How to control the current? How to control the current distribution? That depends on how you design the antenna, because different geometry of the antenna form different current distribution. Okay, the different current distribution generate different the field property. Okay, control how electromagnetic field propagate, and it's a special distribution of electromagnetic field. Okay, so let's stop here today. I overrun 5 minutes.